Hello class, this is Mr. Hart, and in this video I want to talk about where the kinematic equations come from. Now, I have a lot of students that talk about how they wish they knew more about the kinematic equations and why they work, but we don't have the time in class to talk about how we derive these equations. And one of the equations we can't do without calculus, but in this video I want to talk about how we can find these equations, how we derive them algebraically, and try and give you some intuition about how they work and why they work the way they do. Okay, so first of all, let's remind ourselves of all the kinematic equations. Okay, so we have this one for position, that's dependent on the initial velocity and the time and the acceleration. We have this equation for final velocity, which depends on initial velocity and acceleration and time. We have this one, that is the position that's dependent on final velocity, initial velocity, and time. And then, of course, everyone's favorite one with the squares in there, the final velocity is dependent on the initial velocity, the acceleration, and the change in x. Okay. Now, I've talked about this in class before, but I envision these kinematic equations as kind of like a ladder, right, where we have our position definition on the very top, and we can derive or find the velocity by its definition, which is the change in x over the change in time, which is like stepping down this ladder into the velocity domain. And then the acceleration is defined as the velocity over time, and that's like stepping down the ladder again. These three definitions are kind of like going down the ladder. And then the kinematic equations help us go back up the ladder. So the final velocity equals initial velocity plus at. It's kind of like going from acceleration back up to velocity. And notice that we times by time there to get that equation. And then same thing here, change in x equals 1/2 v final plus v naught times t. Kind of takes us from change of velocity into position, right? So it's like going back up the ladder. Okay. Now, if you ever take calculus, you'll realize that this is the same as taking the derivative is going down the ladder, and taking the integral is going back up the ladder. Okay. But for now, we're going to try and see if we can derive the kinematic equations without calculus, and kind of imagine what it would be like if we just had these definitions and we were trying to get all the kinematic equations. How would we do it? Okay. So again, let's imagine we don't know any of these kinematic equations to start. We just have the definition for change of x. It's just x final minus x initial. The velocity is change in x over t, and the acceleration is change in v over t. Okay, so assuming we just have those, how would we start? Okay. Well, the first one to find is really simple, and we actually did this one in class. If we just start with the acceleration equation, okay, change in v over change in time, and then we times change in time over to the other side, we get acceleration times change in time equals change in velocity. Then if we use our definition of change in velocity as v final minus v initial, and then we simply add that over to the other side, then we get the first kinematic equation that we can find, which is v final equals v initial plus a times change in t. Okay, so that one's really simple to find, and that just comes from some simple algebraic manipulation. Okay, so there's our first one we found. Okay, v final equals v initial plus at. Okay, the next one we want to find is this one right here, and this is the one and the only one that really takes some calculus to understand, but let me see if I can at least give you some intuition of why this works. Okay, so change in x equals v initial times time plus 1/2 at squared. Okay, I'm going to kind of show you this visually and how I like to think about it. Okay. So here's the idea. If we know acceleration is constant, and that's what we assume for all of the kinematic equations, then if the acceleration is constant, then the graph of acceleration is just a flat line. It stays the same value for the whole time, right? It's constant. If we want to take the velocity time graph from that, we've learned in class that we take the area under the curve to go up, right? You probably remember that we can, say, okay, if I want to find the velocity after 4 seconds, I find the area under this curve or this line, right? And that tells me how much velocity I have at that point. So after 4 seconds and an acceleration of 5, we would expect that the velocity should go up to 20, right? We've done this when we converted between velocity and position graphs. We can do the same thing for acceleration and velocity graphs, okay? And so we can find this velocity by taking the area under this curve. And we know that we should get this kind of linear movement, okay, that goes up like this, right? The velocity is constantly getting faster and faster, because the acceleration is making it go up and up and up. Okay? Now, if we take the area under this velocity curve, we also can find the position that way. Okay? But the real question is, why does this position curve? Well, if you think about it, as the velocity goes up, right? If this was a constant velocity graph, we would expect a linear position graph. But since the velocity is going up linearly, then the position is going to go up and up and up, and it's going to get faster and faster and faster, right? So we expect it to cover more distance as it goes along, okay? And to really see why that is, you need calculus, but the point is this is going to curve. So when we had some constant value here for the acceleration, then we find that the velocity graph has a single time value that is linear, okay, like this. And then for the position graph, we find that it is dependent on the square. We get a quadratic, okay? And again, once you get into calculus, you'll see why that is. But for now, the intuition is a constant acceleration leads to a linear velocity, which leads to a quadratic position time graph, okay? So when we have this equation down here, that's what we're seeing. So we see that it's dependent on the acceleration times the t value squared, which is this quadratic graph we see, but it also depends on the initial velocity times the time. But remember that the initial velocity was probably a linear value, so when we times that by time, we also get this quadratic value added to it. Now again, I'm doing a lot of hand waving here. That's not quite why it works this way. You really need to take calculus to see why this is the case. And again, a lot of students say, well, what about this 1/2? Again, you can't really see why that is the case until you take calculus, okay? But hopefully you have a little bit of intuition here of position graphs should be quadratic in nature, and that's why our equation is quadratic, okay? So if you really want to see why that is the exact form it is, take some calculus, okay? But let's move on. So now we have this equation here and this equation here. Let's go to the next one, okay? And the next one's actually really cool. This comes from a cool fact about quadratics, okay? We find that the change in x is equal to 1/2 plus the final velocity plus the initial velocity times time. But notice that final velocity plus initial velocity over 2 is the same as the average velocity over that time, okay? So why does this work, okay? This comes from, again, quadratics. If we take the slope at 2 points of a quadratic, okay, so I'm going to draw this line here, and let's say this line there, okay? That's the slope at these 2 points. Let me do a different color here. That's the slope at these 2 points on the quadratic, okay? Now the cool thing is the average of these two slopes, if we drew a different line, is actually the slope that would connect these two dots, okay? Which is kind of cool. So this blue line slope would be the average of that slope and that slope. But not only that, another cool fact that's not directly related to this, it's also the slope halfway between those 2 points. So if we mark this point, it's the slope halfway in between. So kind of cool to think about and really interesting to see. But the point is, if we can get this average velocity, then we can kind of short step this quadratic and just travel along this blue line to get to the final value, okay? But we can also prove this algebraically, okay? So if we start with this equation right here, change of x equals v naught t plus 1/2 at squared, and the acceleration equals change in v over change of t, which we've seen before, right? One of our definitions, okay? Let's try plugging in acceleration into a right here in this equation. If we do, we get change in x equals v naught t plus 1/2 change in v over change in t times t squared, okay? I should just use t rather than change in t, but notice that we can cancel one of the t's out. So we'll be left with change in x equals v naught t plus 1/2 change in v times t, okay? Now I'm just going to rewrite this a little bit differently. I'm going to put the change of v and the t on top with the 1. And so when we do that, we end up with this. Okay. Change of x equals v naught t plus change in v times t over 2. And now we can separate out the definition of change in v. Okay. So if we just think about the pure definition of delta, right, it's v final minus v initial times time over 2. Okay. Now that's good, but in order to add these two together, okay, I need to have the same denominator. So I'm going to say change in x equals, I'm going to times this by 2 on both the top and the bottom, 2 v naught t over 2 plus v final minus v initial times t over 2. Now we can combine those two, and we're left with change of x equals 2 v naught t plus v final minus v naught t over 2. Now we can say change in x equals 2 v naught t plus, let's just times this out, distribute the t, v final t minus v naught t over 2. Notice that I have 2 v naught t minus a v naught t, so we get just a single v naught t plus a single v final t over 2. And then when all is said and done, we're going to pull out the t, we're going to group the v naught and the v final, and we're left with our definition. Change of x equals 1/2 v final plus v naught t. Okay? So that's really cool. Or you can just algebraically manipulate that because of this cool property of quadratics, and we're left with this equation right here. Okay? All right, so we're almost there. So now we got this one, and this one. Time for the v final squared equation, everyone's favorite. And this one just comes from a lot of algebra, right? The idea is this one doesn't depend on time, right? Just change of x. And we know that change of x is quadratic in nature, so there's going to be some squares involved in here. Okay? But it's not too bad, so stick with me. Okay? Let's prove it. So now we have this equation, change of x equals 1/2 times v final plus v naught times t. If we manipulate this, really it's not a big manipulation. We're just going to rewrite it like v naught plus v final over 2 times t. And then likewise, our acceleration equation is change in v over t. If we manipulate that to solve for t, we get v final minus v naught over a, right? And then also write the change in v definition. Okay, so what we got to do to get rid of time is we got to plug in our definition of time right here, or not our definition of time, but this solved version for time, and plug it in for t right here. Okay, so when we do that, we're left with this. Okay, change in x equals v final plus v naught over 2. That was the first part. And then we replace t with the v final minus v naught over a. Okay, from there, let's move the 2 and the a to the other side. Okay, and we are left with v final plus v naught times v final minus v naught. Okay, now if you remember algebra, we're going to have to do FOIL method, right? We're going to have to distribute this twice basically to multiply this thing out. Okay, now I've already pre-done this, and when we do that, we end up with this. 2a change in x equals v final squared plus v final v naught minus v final v naught minus v naught squared. Okay, that's the full form of multiplying that all out. But notice the nice thing is that when we do that, everything right here, this and this, just subtract from each other. And so we're just left with v final squared minus v naught squared. Okay? Then simply from there, we just add the v naught squared to the other side, and we are left with our final equation. V final squared equals v naught squared plus 2a change in x. Okay? So there you go. Now there's not a ton of intuition for why this one works. It's just canceling out the time. But again, think about it in terms of change of x is a squared value, and so it's going to have some squares in there, right? Because we should expect this nice curve. But other than that, it's not very intuitive. But there you go. It's a very nice equation to have and to use when you don't have time. Okay? And that is it. That is all the kinematic equations. Okay? So hopefully this gave you a little bit more of a sense of why these things work the way they do and how we found these and where we get these. And again, if you really want to understand this one, take some calculus. But I hope you enjoyed that. I hope this gives you a better understanding of why we use these, and thank you for watching.